All right. Welcome to the last video. We're going over your test 3 reactions, mainly going over chapter 16. So that goes over your reduction reactions and the reactions from like ANCO. We're also going to look at some reactivity and then the Grignard reagents. All right. So let's go ahead and jump into it. Let me share my screen. There we go. All right. So we're going to do a quick little recap of the reactions we had last semester. So if you remember your mild oxidizers, remember like PCC, your bleach. This is separation. They're not actually together, but PCC is a mild oxidizer on its own. And there another mild oxidizer is sodium hypochlorite bleach, acetic acid CH3, COOH, then maybe some heat, stuff like that. And your strong oxidizers, if you remember, like your Jones reagent H2CR4 or like K2MnO4, just another variation. It does the same stuff. But the point is you just have strong oxidizers. So if you have a primary alcohol, right, this essentially converts to that, oxidation creates another carbon-oxygen bond. So if this carbon right here would create another carbon-oxygen bond, well, the first step, or the first stage would be an aldehyde. All right. For strong oxidizer, we're going to up the ante and create 2 more carbon-oxygen bonds. So originally you only have this singular 1 carbon-oxygen bond, but here we have 2, here we have 3. All right. Now for secondary, you don't have that many beta hydrogens. You only have, or not beta, alpha hydrogens. You only have 1 compared to the 2 that's offered here. So if you have 2 hydrogens that could be lost, you can replace them up to 2. You can replace up to 2 carbon hydrogen bonds with 2 carbon oxygen bonds. But here you only have 1. You can only create another carbon oxygen bond, and that would end up to be a ketone because we lose this hydrogen and we create another bond right there. And once we have the product, well, there's no other hydrogen that can be lost. So ketone is pretty much it. And same thing with strong oxidizer, because again, it does the same thing. You can't rip off more hydrogens that aren't there. And the basic one, tertiary alcohols, well, there are no hydrogens on that alpha carbon at all. So there's no hydrogens to rip off. You can't really make any more carbon oxygen bonds. There's no reaction. Another good reaction is your ozonolysis, right? You have your first step, O3, negative 78 degrees Celsius. And then you have like DMS, right? This is your ozonolysis where you essentially take a pair of scissors and you just cut it down there and you just stick 2 oxygens in there. And by definition, that's an oxidation reaction. You create 4 carbon oxygen bonds. And ozone, as you'll find out if you take upper level chemistry classes, it's one of your strongest oxidizing agents ever. Among your strong oxidizing agents, naturally, you have fluorine and, wouldn't you know it, oxygen in real life. And the next one is your general configurations or transformations from alkynes. So if you have a terminal alkyne, well, if you react it with BH3 or RBH, THF, NaOH, H2O, HC, no, that's supposed to be the peroxide, HOH, you will create an aldehyde. But for the ketone portion, you just need H2O, HgSO4, H2SO4. This should ring the bell from last semester. So from last semester, these are the ways that we could still make ketones from before. Now let's bring a new type of reaction, is the ANCO reaction. So the general pattern is, well, if you have any kind of carbonyl, this carbon is partially positive, right? And these electrons here on that carbonyl oxygen have an affinity for protons. So if you have a nucleophile that wants to attack, well, a nucleus, an exposed nucleus because it's partially positive, and you also have an oxygen that likes to be activated by snagging onto a proton somewhere, we just call that molecule, well, you usually have reactions. So if you have something like this, let's say we're reacting it with, KCN, a weak base, and we're going to activate it with some HCl. The HCl is just to activate that carbonyl, stuff we've seen before. Well, your product would look something like this. Where that CN attack that. And there's also another step before that where the oxygen grabs that proton. Again, this is just the general reactions. I'm not going over mechanisms. You guys can do that on your own. Next one, if we had a ketone, let's react it with NaSH. Let's again throw in an acid catalyst, a weak base with an acid catalyst. We get something like this. SH, again, where we protonate that carbonyl oxygen. And we have a nucleophile that attacks there, right? Now let's bring back an aldehyde. What if you had a strong base, right? Strong base where the first step was NaOCH3, all right? Well, that would create something like this, HO. OCH3, but that is very unstable. So we usually treat it with HCl to reprotonate it and ensure that we have a stable product. There we go. This is what we got. Now let's do it again with a ketone. Let's do it with another weak base, HOCH2CH3. Well, even if weak base, well, we can still treat it with acid because as a catalyst is going to make the reaction go forward. Once you know the components, you can kind of figure out what's going to happen. HOCH2CH3. Right? And then what if you have a ketone? Well, what if you had just water and HCl? Right? Well, you would have an anchor reaction because, hey, look, we got a weak base, but we are activating them. Let me erase these. Let's keep them consistent. We're activating them with acids. Oh, the arrows are in the wrong way. We're activating them with acids so that these carbonyl carbons are more susceptible to nucleophilic attack. So if our nucleophile is going to be H2O, well, H2O is just an OH moiety on an oxygen or on a hydrogen. So it would look something like this. Right? Where that H came from that HCl, your water attacked there, and in the end, it's deprotonated in a lingering proton transfer step, something that we have done in many mechanisms. Again, I'm not going over the mechanisms. This is just stuff to put in your flashcards or just to help with your problem sets and just to go over stuff you'll need for test 3. Well, let's start kicking it up a notch, okay? So what if we had NaCN HCl, right? And we know that that's eventually going to adhere to this aldehyde carbonyl carbon. But what if you had a second step? A second step that was H2O, HCl, and heat. Now you might be thinking, well, what the heck am I doing? Well, again, look at the numbers, right? Let's do one at a time. We know that, hey, this is what we're going to get. Okay, look at the pattern. They break the carbonyl carbon, and that nucleophile attacks that carbonyl carbon, and hey, look, you now have a new bond, new carbon-carbon bond. Now, the second step, H2HCl, does that affect any of these functional groups? Well, yeah, it does. It affects the nitrile group, because if you remember, if you treat the nitrile group with an acidic solution, or just hydrolyze it, better sense, you create carboxylic acid. So this is what you get. All right, you get an alpha hydroxy, 1, 2, 3, 4, 5, pentanoic acid. Now let's throw a different reagent. DIBAL-H. You don't need to know the mechanism for this. And we usually treat it with, again, H3O plus, or you can do HCl. It doesn't matter because it's synonymous chemistry. Well, when you have an ester, it just creates that into an aldehyde. So you're reducing it. You're removing a carbon-oxygen bond, and you're creating a carbon-hydrogen bond. That's the definition of a reduction, right? So you don't need to know the mechanism. You just need to know that DIBAL all right, just creates an aldehyde. That's the only way we can make an aldehyde from a carboxylic acid derivative, right? We can make aldehydes again from stuff like this, or this, or this, many different ways, right? But you might be thinking, hey, can I do this if I had an OH, right? Instead of an ester, what if I had a carboxylic acid? Well, not exactly. I think there's a lot of chemistry that kind of interferes with it. And I was fact checking with Dr. Berg, and he says it's not going to really happen. What he will throw at you guys on the test is if you have an ester and you're treated with DIBAL, it will become an aldehyde. That's the extent he's going to go. So from that assumption, we can assume, hey, for this class, let's just treat it as if esters are the only things that can react with DIBAL. So if I'm trying to get this into an aldehyde, we need to make it into a treatable form. So we need to make it an ester. So if we hit the first step of HOCH3 HCl, we know that that initially makes OCH3, right? Methyl acetate. That makes an ester. And then we treat it with DIBAL. H3O plus. Now we get the aldehyde. All right, so that should be pretty straightforward. Now let's get to the Wittig reagent. So the Wittig reagent, it's kind of like the Gabriel synthesis. If you remember the Gabriel synthesis, you had something like NaOH. For now, pretend that's the Gabriel reagent. NH. So like that. And then you had like a carbon chain R, and then some kind of leaving group BR, then you had H2O, HCl, NaOH. And if you remember the last video, this is the main thing you're looking for, where these are pretty much just the stabilizing reagents. The Wittig reagent is kind of like that, where you have treat it with your ylid, 1P. And remember, pH is phenyl. I don't want to draw it out in all honesty, so I'm just going to keep it as phenyl. And butyl lithium, 3-cyclohexanone. And this is just the ketone that I'm reacting with. So if I were to redraw it, this is cyclohexanone. Okay. So with the Wittig reagent, you create an ylid with this. Watch Dr. Berg's video, and if you're confused on what the Wittig reagent does. But essentially how I see it is once you have a leaving group attached to a BR, this BR is going to be thrown off. Whatever's in here, I replace with that O. Right? Here, let me erase this. I don't know why I drew that. You replace that O. So product would look something like this. I don't know why I keep drawing that. All right. Instead of the oxygen, CH3. Another way you can draw it is just, I keep drawing that. I apologize. Something like this. Again, oh, pardon. Excuse me. Yeah, okay. Whatever's here attached to your leaving group, you just stick onto there, and that's what we have right here. Right? I just have an ethyl group replacing the OH. So let's actually throw it out. So what if we had our Wittig reagent as this? CH3CHPPH3. And remember, something I want to note, these first two steps just create your ylid. All right? And over here, I just essentially condense that. I already have my ylid. I don't need to treat it with anything else. I already have that ylid there. And I already have my reagents. So I just combine them. Well, hey, look, I have another ethyl group. So I have that ethyl group and I have that oxygen. I just replace that oxygen in that ketone or aldehyde with that ethyl group. CHCH3. Another way you can draw it again is just as right. Something like that. That works. Okay. So let's say you had something like this, where you have an isopropic group. This, if I were to draw the line diagram, looks like this, where you have a carbon here, CH3, CH3, and a CH. All right, methylene. All right, now let's say for that BR, if we were to start out with 1, let's create our ylid, BPH3, 2, again, butyl lithium. This is what we used to create that ylide, right? And 3, let's make 3 our reagent. Let's say acetone. So if we know, hey, we have this Br, carbon, 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 and acetone, like this, carbon, carbon, carbon. Well, if we know that this essentially creates our ylide, all right, create something that looks like this, a big complex, and we have our acetone, well, we just replace that oxygen. So if I were to redraw acetone, but instead of that oxygen, I draw that isopropyl group where that Br was attached. Now I put them together, and this is what they look like, where this isopropyl group was derived from CH3, 2CH, and this complex right here was derived from your acetone, right? So hopefully that makes a little bit more sense. So now we've been throwing around oxidations and reductions. Let's go over just what the heck I'm talking about. So the most reduced form of carbon is going to be methane. The most amount of carbon-hydrogen bonds. So creating carbon-hydrogen bonds relates to reduction. Carbon-oxygen bonds relates to oxidation in organic chemistry. So we're not looking exactly at loss or gain of electrons because you'd have to look at the oxidation numbers. But for this one, you're just looking at it as a fact. You oxidize it. Let's create a carbon-oxygen bond. Let me space this out a little better. Primary alcohol is methanol. Let's oxidize it again, all right? Let's remove, so in this step over here, we removed one of those and replace it with an oxygen. Actually, we replace this one with an oxygen, all right? Now for the second oxidation, let's remove another one of these H's to create an aldehyde. Then from an aldehyde, well, do we still have hydrogens to give up? Yes, we do, right here. So we're going to give that up and replace it with a hydrogen. C, OH. And now let's take a look. Do we still have a hydrogen we can give up? Yes, right here. Carbon dioxide. Where that carbon right here no longer has hydrogens to give up. So methane is the most reduced form of carbon. Carbon dioxide is the most oxidized form of carbon. And the intermediates are the stuff we've seen: carboxylic acids, aldehydes, alcohols, all deal with oxygens. So your oxidation reactions go this way. Oxidation reactions. So just to throw some oxidation reagents that you have seen so far: H2CrO4, K2MnO4, PCC, NaOCl, CH3, COOH. An argument could be made that it's heat because we can decarboxylate something. That's a special situation though. And ozonolysis. Right? So like if I'm trying to get from the aldehyde to the carboxylic acid or the alcohol to the carboxylic acid, well, I just treat it with H2CrO4 to go down the line. And what if I wanted to go reverse, right? That would mean we do the reduction reactions. The ones that we've already seen, well, your Grignard's a reduction reagent. Br, H3O plus, because that the carbon ion they create, or the organometallic creates, will attack a carbon oxygen bond. So you remember your like ethylene oxides or just simple carbonyls. Well, these are prime targets for your Grignard reagent, and it'll destroy a carbon oxygen bond. So by definition, it's a reducing reagent. Reducing agent. H2 radionickel. H2 PD on C. Your Wolff-Kishner reduction, NaOH, 0 degrees Celsius, because remember you had like acetophenone, right? Well, if you treat it with your Wolff-Kishner, you obliterate that and you create like this, where you essentially just replace these with hydrogens. And now those hydrogens persist here. And look at that, we destroyed carbon-oxygen bonds and replaced them with carbon-hydrogen bonds. So that's how you should be looking at reducing reagents, reduction reactions. And the two new ones that we introduced, LiAlH4, you can call that LAH, or NaBH4. This is going to be mild. This is going to be strong. Strong reducing. Strong. Mild. They're different variations. So now let's use what we know and just throw it at some of the reagents we've been seeing. So again, just to highlight, reductions, we add hydrogens to pi bonds. Specifically, we add them to carbon-oxygen bonds, but most of the time we're going to see them as pi bonds because that's what we've been dealing with: carboxylic acid derivatives, aldehyde ketones. So if I were to redraw that list, we have carboxylic acid derivatives, ketones and aldehydes, and you have your normal pi bonds, not exactly carbon-oxygen bonds, but still double bonds that can be hydrated, alkene, or hydrogenated alkynes. Now, the distinction I want to make is that these are relatively easy to reduce, but carboxylic acids take more power, right? They need a lot more reduction potential in order to destroy them. All right, so if you have a mild oxidizer like NaBH4, this one can only reduce ketones and aldehydes, right? So you're going to get something like this. We know that, okay, hey, we have this carbonyl carbon and this carbonyl carbon. This one will not react because that's a carboxylic acid. This one will, that's an aldehyde. So you will create something like this, OH and an H, and this will remain unchanged. You're thinking, well, why is it an OH? Well, look at your notes. You have a hydride that's coming into here. But essentially, you can also look at it as, well, if we have two carbon-oxygen bonds that can be destroyed, well, what happens if we destroy one? Right? Let's pretend we destroyed one of these and replace it with a carbon-oxygen bond or carbon-hydrogen bond. And then also we protonate that because there are free protons or hydrides floating around. Well, hey, that's what we get. Okay. Now let's throw LiAlH4. Let's up the ante. Okay. Well, if we had this, it'll reduce both. Carbonyl carbon, carbonyl carbon, both will react with LiAlH4. Those are supposed to be check marks, by the way. So you'll get something like this. I'll retain my carbons because your reducing reagents don't destroy carbon and carbon bonds. OH, H, OH, H, H. Okay. Now, what if you were to treat it with uncommon stuff, like an aldehyde or an acyl chloride? LiAlH4. No exceptions. Hey, this will react. This will react. Carboxylic acid derivatives and ketones will react with LiAlH4. So, stranded carbons, we have 3 carbons. 1, 2, 3. OH, let's change that. H, 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 OH. We have a diol. Okay, now let's have it over here. Let's, again, reemphasize, hey, we have a ketone and a carboxylic acid derivative. LiAlH4, NaBH4. LiAlH4 will obliterate both. Okay. OH, H, H, OH, and H. But NaBH4, well, it'll only react with this carbon. It'll leave the other one alone. So it's the exact same deal, but this is left alone because it's not reactive enough or is not strong enough of a reducing agent. OH, H is your product. Now, here's the weird exception, right? LiAlH4. If you have an amide, it will not obliterate that and make it into an alcohol like you've been seeing. Like all of these have been turning your carbonyls into alcohols essentially. Your main deal that you've been seeing is you're turning these into that, which follows a reduction reaction pathway. We're going backwards, or we're going this way. In here, LiAlH4. Here, NABH4, right? Well, here, it's a little different. This is what the product looks like. You know, hey, carbonyl, both will react. You will produce OH, H, H. Here's the kicker. Instead of OH, it will leave the primary amine alone. Well, it wasn't primary to begin with, but it'll leave it alone. All right. It will retain the nitrogen. That's the weird thing. All right. So amides are a little bit more resistant because they're not very reactive in the first place. So when you see these, keep this. So that's the one exception I want to make clear, because look at all of this you have to deal with, right? If you have to know one thing, your amides don't completely react, right? I know. It's a little bit of a booty cheeks. All right, but let's move on to Grignard. So Grignard, you have your Grignard reagent, some kind of R group, and an MgBr. Essentially, that creates a carb anion. Okay? Give me one second. All right, we create a carb anion. Well, if we know that these are reducing reagents, right? They really like to obliterate. It likes to break carbon oxygen bonds, right? So we have three different scenarios. What if we have an aldehyde, right? And then a ketone, or no, another aldehyde, and we have a ketone, H3, right? You might be thinking, well, if these are reducing agents, where are the carboxylic acid derivatives, right? Well, we can see that. We will see that. But remember, carboxylic acids, like with the OH moiety, they cannot, because remember, protic groups cannot react with your Grignard reagent because it's a very basic carb anion. It's just going to rip the proton off, right? But hey, let's take a look. So if you have, R, let's say it's a CH3 carb anion, right? You have your MgBr salt somewhere in the solution, right? What's going to happen? It's going to attack that partially positive carbonyl, break that, and form something like this. So that formaldehyde, I'm just going to draw the CH2 as something like this. CH2, right? This comes that, right? OH, R. Because essentially, first off, that double bond broke to become this. And again, when we have a Grignard reagent, we always treat it with acid to make that oxygen into an alcohol. So essentially, what we just added, well, this is our Grignard, right? And that H is from some kind of H3 as catalyst H3O plus. Okay, let's do it again. H3O plus. And let's have that R group attack here. Well, we have our CH3 R group OH, right? This is just that. Then oxygen. So that oxygen, well, we add that proton from the H3O plus and that R groups from our Grignard reagent. Let's do it again with the acetone. H3O plus. CH, no, it's not CH. It's going to be CCH3, CH3, R, OH, right? Nope, not that. These are from our original acetone components, while our H3O plus and our R group that are added together are Grignard. Let's take a look. Well, formaldehyde, right? Well, there's only two hydrogens, and if there's only two hydrogens there, well, it makes a primary alcohol. So formaldehyde creates a primary alcohol. While an aldehyde, just any aldehyde in general, because, for an aldehyde, you need one H there, and then you need an R group here. Well, that R group is over here, right? And we added another R group. So technically, if we have one R group already there, and by the Grignard, we add another R group, well, any aldehyde becomes a secondary alcohol. And what if we have a ketone? Well, ketone we add here, it already has two existing R groups, and we add a third one. Well, hey, that's a tertiary alcohol. So ketones create tertiary alcohols, right? Now let's try to do it with an ester. So we talked about that. It can also destroy carbon-oxygen bonds and carboxylic acid derivatives, right? Not carboxylic acid because it's acidic, but let's treat it with our Grignard reagent. So this is going to be our carb anion. It's going to be a benzophenyl group. And again, let's treat it with H3O plus. So if we have two servings, well, we just follow the same kind of rules where, hey, we just attack that right there. So we get one serving CH3, C, and then that phenyl group that we added. And note, even though we have a Grignard, that OH or that carbonyl carbon is retained, right? It's retained. But if we were to do two servings, or this could be drawn as excess, is excess, you see how it, yeah. Well, now we follow our normal Grignard reasons. Well, hey, we have a ketone now, right? So ketone is essentially like, well, that second serving is essentially adding more Grignard to that ketone you just made in the first serving. So we'll get something like this. Remember, our pHs are our R groups. There you go. Now you create a tertiary alcohol. So we create a ketone here, right? And if you know from up here, well, ketones, if you treat it with another Grignard, ketones make tertiary alcohols. So these are the patterns they have to see. Now, that's a lot, but I do have a, I don't know, just a generalized page that summarizes all of the different reactions. Right here, I just reevaluate or just summarize what I showed you about, formaldehyde becoming primary, aldehyde secondary, ketone tertiary. And here again, you have a carboxylic acid derivative, something that's not protic. One serving, snag attack, you form a ketone. Second serving, you create an alcohol. And, well, hey, carbon dioxide, that's the most oxidized form of oxygen. You have carbon-oxygen bonds you can destroy. So if you destroy one of them, well, C, OH, our group, well, that looks like a carboxylic acid. And what do you know? We do create a carboxylic acid. So essentially, whatever that MgBr is, replace with a carboxylic acid if you were to do CO2, right? Now let's get to the final section. Oops, final section. We're looking at stability. So if you're looking at the delocalization of electrons, either being pulled away from that carbonyl carbon or an alpha carbon, which you will care about a lot more later, let's talk about some big concepts. So if your resonance stability is greater, so the greater the resonance stability, right, the less the nucleophile reactivity. What I'm basically saying is that carbonyl carbon is more or is less partially positive. All right, so let's look over here real quick. So if you are asked out of these three, which one reacts fastest with a nucleophile, right? Fastest with a nucleophile out of the four. Out of the four, which one reacts fastest with a nucleophile? So remember, nucleophiles want to attack here, these carbonyls. Well, let's look at what we have. Well, look, we have benzene rings and we have different groups. And if we know that table from test one, aniline is an electron donating group, is a very strong electron donator. All right. Chlorine is a mild electron withdrawing group. Fluorine, same kind of spiel. And alkyl groups are weakly donating. So if we know, hey, if these are donating into that electron, if they're donating electron density into the system, well, this is not as partially positive. They decrease in partial positivity because again, the electrons are being delocalized. They are they're being pulled into that carbonyl carbon. So they're not going to react as fast as the nucleophile. So if groups are donating electrons into the carbonyl carbon, they do not react as fast with nucleophiles. So now let's look at electron withdrawing groups. Electron withdrawing groups pull electron density away, right? So this carbonyl carbon becomes more partially positive. The electron density is being pulled away. You already have a carbonyl carbon with two oxygens here. Carbonyl carbon with two oxygens pulling electron density away. And now you have another group pulling even more electron density away. So now the question is, which one is stronger? Well, look at your chart. Which one is more deactivating? Well, that would be chlorine. Chlorine is more deactivating. So if chlorine is more deactivating, well, this is ranked first for most reactive. Then fluorine. Then out of these two, well, which one's more deactivating? Well, even though it's not deactivating, it doesn't activate as much as aniline. So this would be the ranking. Okay. And you're welcome to rewatch the video. But before we get on to this, let's look at this reactivity chart that I made. So for snack reactivity, this is the stuff that you have already seen, right? Where you have carbon or carboxylic ester. It's isochlorides and anhydrides are so unnatural, they don't even need an acid catalyst. So they will always react with your snack reaction just really fast. Next are your esters, then your carboxylic acids, then your amides. Carboxylates, they will never react because look how bad that leaving group is. And these ketones and aldehydes, they don't even do snack. So you can just ignore them. So you're looking at snack reactivity. It's the stuff we've been dealing with. This is the list. Isochlorides, anhydrides, so your unnatural ones, which is why you have a bunch of arrows or greater than signs. And then your carboxylic acid derivatives, right? Now for ANCO, well, it's the same kind of spiel, but hey, now we're just essentially taking this group that we shunned out, in the snack reactivity and just placing them at the front of the line, right? So now they are here. For ANCO reactivity, isochlorides and anhydrides still react the fastest, but now we have aldehydes, then ketones, and then everything else for ANCO reactivity. So now you have snack reactivity. Snack reactivity, you look at this list. ANCO reactivity, it's the same list, but you now have to consider aldehydes and ketones. And then for nucleophile reactivity, you're just looking at the delocalization, all right? You're just looking at electron density being pulled away or to that carbonyl carbon. So again, just to reemphasize, you have three types of stability or reactivity. You have snack, ANCO, and nucleophile. This, you look at resonance or the electron density. This one you look at the chart or the list, and this is the same list, but now you consider aldehydes and ketones. So now let's answer these questions. Which one of these reacts fastest with a nucleophile? Well, which one's the most deactivated? Well, you know that amides and OHs put some electron density into there, while chlorines are only deactivating group. So we would consider chlorine. And even what's confounding the fact is, like, look at the reactivity over here. Even then, we see that isochlorides are the most reactive. So no matter what, all the answers point to here. All right. And we know that this is obviously going to be the worst one, because on top of that, well, if we look at the reaction beyond, it might react with a nucleophile, but look at that leaving group. The leaving group's the worst of all. So we know for a fact that's not going to happen. Now, which of the following reacts the fastest with ANCO? So ANCO, well, look, acyl chlorides, no. Acyl chlorides, there are none there. Anhydrides, none. Aldehydes and ketones, yeah, we have ketone, aldehyde, aldehyde, and we have an amide. Well, if we know that amides, well, hey, look, amides are at the bottom of the list. We can go ahead and consider this one's not going to be it. So out of these three, which one's the most reactive to ANCO? Well, if we know, hey, aldehydes are more reactive than ketones, we know it's not going to be the ketone. So now out of these aldehydes, which one is it? Well, you look at steric hindrance, right? The accessibility of that positive, partially positive charge to that nucleophile is based on the reactivity. Which one reacts fastest? Well, which one's more accessible? This one's more accessible. So it would be this one. All right. Yeah, that's kind of it. Just want to make sure. You should be able to do most of the questions for your problem set. And if not, anything I missed are in your notes. I just mainly went over the stuff you mainly need to know for the test. I guess that's it.